So we'd like to go over a modeling example now. And the example we'll choose is we want to design a suitcase that can withstand a drop from an airplane. We'll always begin a modeling exercise by stating the model assumptions. This is important because later on, if we find some problem with the model, we can come back to the assumptions and see whether they were correct or not. This model will have two assumptions based on the suitcase, that its geometry is 0.3 meter on a side, a 0.3 meter cube, and that it has a mass of 30 kilograms. And it'll have one geometric constraint on where the suitcase is dropped from. It'll be dropped from a 10,000 meter altitude. And then, as far as analyzing it, we will assume that the Freefall equations from your high school physics will suffice to model speed. Okay, so the idea is we drop the suitcase from the plane. It's going to hit the ground. We're going to have to try to see what kind of velocity it hits the ground with. So let's invoke this high school physics knowledge that kinetic energy at impact is equal to potential energy at the drop. Energy is conserved. Let's see what kind of speed that gives us in this simulation. We begin by writing down the equation for kinetic energy. The kinetic energy is equal to 1/2 the mass times the velocity squared. And the potential energy is simply equal to the mass of the suitcase times the acceleration of gravity times the height from which the suitcase is dropped. And if we set these two things equal to each other, we get that the velocity squared is equal to 2gz. Or if we put in for gravity 9.8 meters per second squared and height 10,000 meters, and we take the square root to find velocity, we'll find that v is equal to approximately 440 meters per second. And that, it turns out, is about 1,000 miles per hour. A 1,000 miles per hour, that's faster than the speed of sound, and that just doesn't seem right. So here's a tip for engineering modeling. When you come up against a situation like that, if it doesn't seem right, you should be suspicious. And in fact, if the answer doesn't look right, it probably isn't right. The model is not useful unless you know how much to trust it. So in this case, what's wrong? The model has low fidelity and it's missing something important. So in this case, what's wrong? The model has low fidelity for this application. It's missing something important about the physics of the real case. And I think you know what it is. It's missing drag. Energy dissipation due to drag is slowing down the suitcase as it falls from the sky. So let's take a look at that. We know that the gravitational force is independent of velocity. In fact, the gravitational force is just mass times gravity, the mass of the suitcase times the acceleration due to gravity. And now we've uncovered that there's an opposing force to the gravitational force. And this opposing force, we can describe it as being proportional to velocity squared. A specific equation for the drag force is that the drag force is 1/2 times the density of the air through which the object is falling times a dimensionless coefficient of drag times the cross-sectional area of the object that's falling times the velocity squared of the object that's falling. And this force always opposes exactly the velocity. So the question is, when in our model could we ignore drag force? Well, the answer is pretty straightforward. When the drag force is much less than the gravitational force, we can ignore it. So in our case, we know that the gravitational force is about 300 newtons, 30 kilograms of mass times 9.8 meters per second squared of gravitational acceleration. And then we can calculate the size that the drag force would have to be much smaller than that. In particular, we can write that if the drag force is much less than the gravitational force, or 10 times less than the gravitational force, then the velocity squared has to be 2 times mass of the suitcase times gravity over 10 times the density of air times the coefficient of drag times the area. And so we end up with a velocity that needs to be lower than 16 meters per second for us to safely ignore drag force. Now, we calculated a drag force of 440 meters per second when we ignored drag. So that is much, much higher than 16 meters per second, which means that drag force cannot be safely ignored in this application. One place where it might have been safely ignored is when Galileo was dropping 2 balls off of the Leaning Tower of Pisa and trying to convince people that they would land at the same time. If those balls had been subjected to significant drag force, they would not have landed at the same time. In fact, the heavier ball would have dropped faster, as predicted by Aristotle incorrectly. So we've got these forces. Now what we'd like to do is figure out how do we find the velocity at any given time. Well, to do that, we need to solve Newton's law, which says that force equals mass times acceleration. The net force equals the mass times acceleration. Net force is the gravitational force minus the opposing drag force. And we can substitute in for the mass of the suitcase, the density of the suitcase times its volume, which is L cubed. And we know that the cross-sectional area of the suitcase is L squared. When we plug all those formulas into one another, we end up with an equation for the acceleration as a function of gravity, density of the air, coefficient of drag, the square of velocity, the density of the suitcase, and the length of the suitcase. Now, we need to invoke one more thing that we know about the acceleration. The acceleration is velocity derivative. The acceleration as a function of time is the change in velocity as a function of time. So we can substitute AT into that, or substitute dv dt into that equation that we just had on the previous slide to get this equation for the velocity as a function of time. What kind of equation is that? Well, it's a nonlinear first-order differential equation. First order because it's first-order derivative in velocity as a function of time, and nonlinear because the term modifying velocity is velocity squared. So this makes the equation nonlinear. It's not trivial to solve. It's actually not impossible to solve, but it's not something that you would have learned in high school. And so we can use a numerical model to solve it. And in our case, we're going to use the numerical modeling software that comes along with MATLAB. It's called Simulink. In the following simulation, we will construct a model numerically that simulates this equation, this nonlinear equation. And when we solve that model, it will produce for us a time history of velocity, and it will do that numerically. So let's move on to the model. In this simulation, we have a Simulink window in which we will perform our numerical simulation. We have a MATLAB window in which we will analyze the results. We have a reminder of our equation that we're trying to model down in the lower left. And then we have the various blocks for the symbolic language of Simulink that we can put into the model. In particular, we're going to begin by modeling dv dt. And if we are trying to get the velocity from dv dt, we need to integrate it. So we'll begin by taking an integrator and placing it in the Simulink window, and we'll move on from there. So the integrator goes into the window. We'll make it a little bigger so we can see it. And now that integrator will work on dv dt, and it will produce v, the velocity. And it will do that numerically, so we won't have to worry about the details of that integration. The rest of this equation involves g, where we'll now have to take a constant out of our block, and we'll set that constant equal to g, and we'll label this constant block gravity. So this is a constant in my Simulink model. I'm going to now try to create the rest of the model, and the rest of the model will include modeling density CD CVT squared over 2 rho LS, but it's subtracted from gravity. So I'll take this symbol, which is a difference symbol. I'll take a plus and a minus, add gravity, go to the integrator, and now I need to subtract this term of density times coefficient of drag times velocity squared. Well, first I need to create velocity squared. So I just take a product block and take the output, which is velocity, and multiply it by itself, which gives me velocity squared. Now I'll drag over a block that will allow me to perform these multiplications and divisions. This is a divide block. I expand the functionality of the block by saying I would like 3 multiplications, 3 divisions. Okay. And now I'll stretch that block out a little bit. And now I simply need to tie in my various constants to that box. First constant is going to be the density of air. And I will label that P sub A I R. Okay. Connect that to the first multiplier of the box. Now I need my coefficient of drag. I'll add another constant block to the simulation. Label this one drag and put the constant to be C sub D. I could put numbers in these boxes, but I want to be able to change the variables in MATLAB, so I just label them with variable names. Now I need a constant 2, pretty easy to put in. I put in a block, I label it with a constant value, which is a numerical value of 2. I'm dividing by that. I need another constant, which is the density of the suitcase. And I'll label that piece of S. Divide by that. And a final constant, which is the length, characteristic length of the suitcase. We know that the suitcase is 0.3 meters on a side. So we will put in L sub S for the suitcase length. And now I have the term, which is rho CD V squared over 2 rho L. And I need to subtract this from gravity. So I take the output of this block and I carry it around to my subtraction line. And now I have constructed the entire simulation. Now what I'd like to monitor is V, the velocity. So I'm going to put in a wire that connects V right into my MATLAB window. And so I need to grab a workspace block from the Simulink. I'm going to label the variable V. And now when I run the simulation in my workspace in MATLAB will be the variable V as a function of time. So what do I do now? I have to set the variables in MATLAB. I'll set the gravity to be 9.8 meters per second squared. I'll set the drag coefficient to be 0.6 dimensionless. I will set the air density to be 1.25 kilograms per meter cubed, which is about the density of air at sea level. I'll set the density of the suitcase to be 1,000 kilograms per meter cubed. That's if the suitcase was filled with water. Pretty heavy suitcase. And I'll set the length scale to be 0.3 meters. Now I simply run the simulation, which is called freefall.sim, freefall_sim. And when I run that simulation, the variable V comes back to me, so I can create a figure in MATLAB and plot the variable V as a function of time. And you can see that the freefall simulation now the suitcase will reach a terminal velocity of about 88 meters per second. So in fact, the velocity doesn't increase linearly. It increases to a point and then slows down. So let's try, now that we have the velocity for the suitcase, let's try to see what happens if we dropped an elephant from the plane. Elephant's much bigger. Going to say the elephant has about the same density as our water-filled suitcase. And so all we'll have to change is LS, the length of the suitcase. An elephant's about, I would say, 2 meters in characteristic length scale. And so I set that variable, and I run the simulation again. I don't have to change any of the blocks. I just run it again, and then I plot it again. And when I plot it, you can see that now the elephant reaches a much higher velocity, going about 225 meters per second, or several hundred miles an hour, by the time it hits the ground. So what did we learn in our modeling example? We learned that it's important to state your assumptions before beginning to model. We learned that success requires careful consideration of the math model's fidelity to the reality that you are trying to model. And we learned that Simulink provides a powerful way to numerically model complex equations. Thank you.